Welcome friends, Igor is here, and in this video we will define the inverse of a square matrix and use it to solve linear systems. We will start by adopting a method for solving linear equations to solving linear systems. Then we will define the notion of an invertible matrix, and we will quickly realize that not all matrices are invertible. Let's get started. Let's hop into a time machine and jump back to our kindergarten time when we used to solve linear equations. Given this simple linear equation, what we do is we multiply both sides of this equation by the inverse of the coefficient that comes with x. In this case, we multiply both sides by 1/3. Then we use the associative property of multiplication of numbers on the left-hand side, and we see that this equation simplifies to x equals 4. This is the unique solution to this equation. And the crucial part of this solution process was the fact that every non-zero number has a multiplicative inverse. Now, let's pretend for a moment that we live in a perfect world, and given a square matrix A, we can find another square matrix B so that matrix B times matrix A is equal to the identity matrix. Then let me convince you that you can solve a linear system with A as the coefficient matrix in exactly the same fashion as we solved a simple linear equation. We start with a linear system in vector form. The left-hand side is a matrix vector product when we multiply the coefficient matrix A by the vector of unknowns x, and we set it equal to the vector of constants b. To solve this linear system, we multiply both sides of this equation by the matrix B. Notice, we multiply both sides on the left by the matrix B. You have to be careful. Matrix multiplication is not commutative, therefore multiply on the left and multiply on the right are potentially different operations. Next, we use the associative property of matrix multiplication, and then we use our assumption that the matrix B is such that B times A is the identity matrix. Identity matrix multiplied by the vector x is simply the vector x, and this computation shows that we have found a unique solution to this linear system. This solution is the matrix B multiplied by the vector of constants b. Let me illustrate this solution process using an explicit example. We have a linear system with 3 equations and 3 unknowns. We represent this linear system using matrix notation, where A is the coefficient matrix, x is the vector of unknowns, and b is the vector of constants. Remember that we still live in a perfect world for now. So what I can do is, I can do a little magic. I'm going to pull a rabbit out of a hat and simply produce out of the blue this 3x3 matrix B. I've done all the heavy lifting, and all I'm asking of you is to check that this matrix B multiplied by the original matrix A results in the identity matrix. Once I gave you the matrix B, this is just a matter of simple direct computation. But now, because of our previous argument, this means that the existence of such a matrix B implies the linear system has a unique solution, and moreover, this unique solution can be computed by simply multiplying the new matrix B by the vector of constants b. You may want to check that I did not fool you here by taking the original linear system and reducing the augmented matrix to make sure that this is indeed the unique solution of that system. Now, wouldn't it be great if we could solve all linear systems in this fashion? Well, this raises a couple of questions. First of all, how did I know that matrix B should be the one that I gave you? There must be a way to figure out what this matrix looks like. But more importantly, is it possible to do for every non-zero square matrix? In other words, given any non-zero square matrix A, is it possible to find the matrix B so that B times A is equal to the identity matrix? I don't know about you, but I enjoyed a couple of minutes of living in a perfect world, but unfortunately now is the time to go back to the real world. This discussion begs the following new definition. Suppose we have two matrices A and B. They are both square matrices of the same size n. Also, let's suppose that the product A times B is the identity matrix of size n, and the other product B times A is also the identity matrix of size n. Then we say that A is an invertible matrix and the matrix B is the inverse of A. We also adopt a customary notation that we have from numbers, and we denote the inverse matrix by using the exponent notation of -1. Notice one important implication of this definition. This definition is symmetric with respect to matrices A and B. Therefore, if B is the inverse of A, then A is also the inverse of B, and we can say that A and B are inverses of each other. Remember that we are back in the real world now? So let's discover right away that not every non-zero square matrix is invertible. Let's consider the following 3x3 matrix A. Let's suppose that it is actually invertible and B is an inverse of this matrix. I am going to take a vector of constants B, which is the vector 1, 3, 2, and I'm going to consider a linear system with the given matrix A as the coefficient matrix and this carefully chosen vector B as a vector of constants. If the matrix A is invertible with the inverse B, then we can apply our newly discovered procedure to see that this linear system has a unique solution. And this solution is given by the vector matrix B multiplied by the vector B. In particular, the fact that this linear system has a unique solution means that the system is consistent. However, in the real world, not in La La Land, this system is in fact inconsistent. This can be easily checked by reducing the augmented matrix of this linear system, and you will see that the last column is a pivot column. Therefore, this system is in fact inconsistent. But if we assume that the matrix A is invertible, it would imply that the system is consistent. The system cannot be both consistent and inconsistent at the same time. Therefore, we have a contradiction. This contradiction was caused by our assumption that the matrix A is invertible. Therefore, the conclusion is the matrix A cannot possibly be invertible. This example demonstrates that while our new method is very convenient, unfortunately it doesn't work every time. It works only as long as the coefficient matrix of the linear system is invertible, and we just discovered that not every non-zero square matrix is invertible. This is in stark contrast with numbers, because for numbers every non-zero number is invertible. Every non-zero number alpha has a multiplicative inverse, which is 1 over alpha. As you see, the situation is more complicated for matrices. Not every square non-zero matrix has a multiplicative inverse. If you found this video useful, and I will cry all night if you tell me you didn't, then please give it a like and subscribe to this channel to see more of these videos. In the next video in this series, we will discover how to compute an inverse of a non-singular matrix using the Gauss-Jordan elimination algorithm. I will see you later.